Today our topic is resistors and Ohm's law, which is the law that characterizes resistors. Over here we have a little image. At the bottom is the schematic symbol for a resistor with these squiggly lines. The resistor is characterized by a resistance R, a voltage drop V, and a current I. And we use the passive sign convention so that the current is referenced positive, flowing into the positive voltage terminal. Now, above that is a picture of an actual resistor that's made for being used in an electric circuit. However, as we'll see and talk about and discuss, any device electrically which has the form of Ohm's law, which is that voltage is proportional to current and the constant of proportionality is the resistance. Any device that satisfies that law is electrically, for the purposes of circuit analysis, a resistor, even though the device itself may be a blow dryer, a DC motor, an audio speaker, an electric range, or something like that. If it satisfies Ohm's law, for our purposes, it's a resistor. So what is Ohm's law? Ohm's law is that voltage is proportional to current, and the constant of proportionality we call the resistance R. We can solve for the resistance as V over I, volts per amp. So this is a resistance. And the units are called the ohm. We use capital Greek letter omega to represent that. 1 ohm is 1 volt per amp. Okay, so that means if we want 1 amp to flow through this resistor that has resistance 1 ohm, we need to apply a voltage drop of 1 volt. If the resistance was 10 ohms, then we would have 10 volts per amp. To get 1 amp to flow, we would need to apply 10 volts. Now we can turn Ohm's law around and solve for the current in terms of the voltage. I is equal to 1 over R times V. And we're going to define G to be 1 over R. And what is 1 over R? It's I over V. It's the inverse of the resistance. This is called a conductance. And it has units of Siemens, 1 capital S. All right, so this is ohms. 1 Siemens is 1 amp per volt. Siemens. Capital S, not the lowercase s we use for seconds. All right, so we can summarize this. V is Ri, or I is GV, where G is 1 over R. And that is our summary of Ohm's law. Now, we know that with the passive sign convention, if we form the product voltage times current, V to I, that's equal to the power that is consumed in the device. If that's positive, positive power is consumed. If it's negative, negative power consumed is actually positive power produced. Let's see what we get for the resistor. V times I, and now let's substitute, because we know the relation between V and I, so we can substitute for V as Ri. So this would be R times I, or Ri squared. Okay, so the power consumed by a resistor is Ri squared. that's never negative. So a resistor can only consume power, never produce it. Or we could have substituted for I in terms of V. All right, I is GV. Okay, so we could have done that. So we have V times GV, and that's GV squared. And since G is 1 over R, we could also have written that as V squared over R. That also is never negative because V squared is never negative. So that shows us again that a resistor can never produce power, only consume it. And the power is going to be proportional to the square of current or the square of voltage. Let's look at an example of using Ohm's law in circuit analysis. Suppose we've got a circuit that has a source, a resistor, and a device called a light-emitting diode, which, as the name implies, produces light. This is an LED, voltage source, and a resistance R. Suppose we're told that the LED, when it's emitting light, has a voltage drop of 2 volts. Our source voltage is 5 volts, and we want to have 20 milliamps of current flowing through the LED. Then our question is, what is the resistance that's required to limit the current in this circuit to 20 milliamps? Well, let's see. Let's call this point A and point B. Kirchhoff's voltage law tells us that the voltage drop from A to B is the same regardless of the path we take. So obviously in this path it's 5 volts. So in this path it must be 5 volts. And well, here's 2 volts. So the remainder of that 5 volts, which would be 3 volts, must show up across the resistor. And now we know voltage for a resistor, and we know the current, because by Kirchhoff's current law, that 20 milliamps in the LED must flow through the resistance. And therefore, we can solve for the resistance. R is 3 volts over 20 milliamps, and that is 150 ohms. So this is a so-called current limiting resistor. We put it in the circuit to limit the current that flows through the LED. Typically, an LED would have some rated maximum current and a corresponding maximum power, and we have to make sure we don't exceed that specification. So this current limiting resistor makes sure that that's the case. Well, let's see. What is the power that is consumed by the LED? Would it be 2 volts times 20 milliamps, and that's 40 milliwatts. And so that's PLED. How about for the resistor? What is the power consumed by the resistor? Well, we could use any one of these formulas, or 3 volts times 20 milliamps, or let's use this formula that it's V squared over R. So that would be 3 volts squared over 150 ohms. And that gets you 60 milliwatts. Of course, then, by the conservation of power, the voltage source must produce the sum of these, which would be 100 milliwatts. And of course, that would be 5 volts times 20 milliamps would be 100 milliwatts. Notice here that the resistor actually consumes more power than the LED. So that's not very efficient, but for small power levels, we don't really worry about that. Maybe this is just an LED on some kind of a control board that just lights up to tell you a certain condition is true. But if we were to use LEDs to implement room lighting, and we had like many tens of watts or something like that here, we would want to use a more efficient way to limit the current. Okay, so that's just an aside. Resistors are generally too small for us to be able to write or print legible numerical values on them. Therefore, we use the so-called resistor color code to indicate their value, their resistance. And here's an illustration of that. This is from the Wikipedia page on resistor values. And there are two common types based on different tolerances, so that we can only build a resistor to within some finite uncertainty, and it usually costs more money to make a more precise resistor. So for lower cost, we could go with this lower resistor here that has on the right a gold band, which is a plus or minus 5% tolerance. If we want more precise resistances, we could pay more. And up here, we've got a brown band, which indicates plus or minus 1%, and we can go even finer precision at greater cost. So the rightmost band there is either brown or gold, depending on the tolerance, and then the remaining bands indicate the resistance value. So for the finer tolerance, the 1%, we need more bands because we have more precision in our value, so we're going to need more significant figures. So we have 4 bands there, whereas we only have 3 for the 5%. In both cases, the first bands, either the first 3 for the 1% resistors or the first 2 for the 5%, give you a numerical value based on these different color codes. Okay, so let's look at the bottom resistor. We've got a blue band here, that's 6. Followed by a gray band, which would be 8, so 68. And then the third band would be the number of zeros, or equivalently, a power of 10. So this is red, so that would be times 10 to the 2, or we could have just put 2 zeros. So 6,800, or that's equal to 6.8 thousand ohms, or 6.8 kilo ohms. For the upper 1% resistor, let's see, we've got yellow, that's 4. Violet is 7. Black is 0. And then we've got number of zeros. Orange is 3. So that's either 3 zeros or 10 to the 3. Of course, that's just 470 kilo ohms. Let's see. Black is 0, brown is 1. If we go back to our original picture of our resistor here, what is this resistance value? Well, we've got brown, that's 1, black is 0, and brown, and then gold, that's 5%. So 101, well, that means 10 is 10 times 10 to the 1. So that would be 10 times 10 to the 1, which is 100. This is a 100 ohm resistor nominally. Plus or minus 5%. 5% of 100 is 5. So it might be as small as 95 ohms or as big as 105 ohms. More likely it would satisfy some kind of like a bell curve, and that would be the kind of the typical width. So this image here, from the same Wikipedia article, shows 12 different resistors, and this would be the 4-band case, and we don't show the gold band here for the tolerance. So let's see, the third band in every case is a black, so that would be the number of zeros, and so that would be 0 zeros. So for the first one, brown, black, that would be 1, 0, 10. Then brown, red, 1, 2, 12, and so on. So this would go 10 up to 82. Then if we change the third black band to be brown, that would add a factor of 10 to all these values. So you'd have 100, 120, up to 820. If we made the third band red, that would add a factor of 100. So 10, 100, or 1,000, or 1 kilo ohm, 1.2 kilo ohms, all the way up to 8.2 kilo ohms, and so on. So we can get different decades of these values by changing the third band, the number of zeros, or the power of 10. So then the question is, well, since we can only manufacture a certain discrete set of resistance values, what should those values be? And you'll notice here, this goes up by 2, this goes up by 3, and then here you're going up by, more than 10. So they're not equally spaced. And that's because in practice, as we'll see when we start looking at resistive circuits, resistance values typically come into play in terms of ratios. So later we'll study the so-called voltage divider, and that has a relation that the output voltage is equal to the input voltage over 1 plus a ratio of resistances, 1 plus R1 plus R2. And so it makes sense to have more or less fixed ratios between our different values of resistances. And the way we do that is the so-called E-series. So we choose a value of big N, which could be 3, 6, 12, and so on. And then we use resistance values from the sequence X sub N is 10 to the 1 plus little n over big N. Okay, so that would be 10 to the 1 plus 1 over n, 10 to the 1 plus 2 over n. And you can see what would happen is that the ratio of xn plus 1 to xn would just be bringing an additional factor of 10 to the 1 over n. So that would be your fixed ratio, 10 to the 1 over n. So, for example, for the E3 series of resistors, this would be n is equal to 3. That would be 10 to the third. And 10 to the third is about 2.15. So each one of the resistances would go up by a little more than a factor of 2. Those three values would be 10, and then 10 times 2.15, which would be 21.5, which we round to 22, and then go up by another factor of 2.15, and round it to 47. So those would be the three values. And you notice here, there's 10, there's 22, and there's 47. So that would be where you would want to have three values per decade. So you'd have 10, 22, 47, 100, 220, 470, and so on. Then you get E6, okay, 10 to the 1/6. That's about 1.47. So the values go up by about 50%. Those values would be, we keep the same three here, and then we add in, going up 50%, we get 15, and we get our 22. Going up about another 50%, we get 33, 47, and 68. So notice what this did. It took these three values and then interpolated other values in between those. So that added now 15, 33, and 68. Then we double big N, and we get the E12 series. 10 to the 1/12 now is equal to 1.21. So these resistances should go up by about 20%. And those values are what are shown here. This is the E12 series. So 20% above 10 is 12, and then so on. So that then adds in the 12, 18, 27, 39, 56, and 82. So there are 12 of those. That's the E12 series. And that is what we use for the 5%. It makes no sense, since these resistances are only known to within plus or minus 5%, it doesn't make much sense to have this 20% ratio down to 10%, because now the difference in the values of the resistances is almost on the order of their uncertainty, so it's not very useful. However, if we go to the 1% resistors, Now we need, we can afford to have a lot more values in between because they are more precisely defined. And in fact, for that, we use the E96 series. We have 96 values per decade. Now, electricity and electric current and voltage, things like that, are invisible to us. And we don't, hopefully, physically interact with them on a regular basis. So they're rather abstract. And it can be helpful, therefore, to make an analogy with hydraulics. So this is the hydraulic analogy for electricity. So first, let's talk about the stuff. When we talk about an electric circuit, the stuff is electric charge. And that has units of coulombs. Okay, so 1 coulomb is the amount of electric charge. That's the stuff that moves around and has a certain number of joules per coulomb and so on. Okay, so this is in the electric case. For the hydraulic case, it's going to be, let's use volume of water. And we'll use the units of liters. All right, so 1 liter. So this is the hydraulic case. Okay, so liters are going to play the part of coulombs. Now, let's see. We have, of course, flow, or flow rate, if you want to think of it that way. So for the electric case, it's amps. 1 amp is 1 coulomb per second. So it's the flow of a certain amount of our stuff every second. For the hydraulic case, it would be, let's say 1 LPS is 1 liter per second. Liters per second could be our flow rate, or gallons per minute, or whatever you want to use, but we'll use liters per second. Okay, so that's just the flow, the rate of flow of our stuff. Okay, so the current is like just the flow of the water. Then we have potential. And that is the volt. 1 volt, and remember what 1 volt is? 1 volt is 1 joule per coulomb, an amount of energy per amount of stuff. Now, let's take for the fluid case, the hydraulic case, let's take 1 kilopascal to be our unit, right? Remember, a pascal is a measure of pressure, newtons per square meter, and so this is a kilopascal, so that's 1,000 newtons per square meter. I said meter per meter, that was wrong, per square meter, per area. Force per area is pressure. And let's see, we can take that and we can multiply by meters on top and bottom, and it's all right that as 1 Newton meter over meters cubed. And then this 1,000 I'm going to put in the denominator as 0.1 cubed. So we're going to write it like this. 1,000 newtons per square meter can be written as 1 Newton meter per cubic 0.1 meter, or that's 10 centimeters. And that's a liter. 0.1 meters cubed is 1 liter. And of course, a Newton meter, well, that's force times distance. That's energy. That's a joule. So this would be then 1 joule per liter. So 1 kilopascal of pressure has the same units as 1 joule per liter. Okay, so this is going to be 1 joule per liter, which is going to be our basically the 1 kilopascal. So the kilopascals will be like our volts, and liters per second will be like our amps. Now, we've just seen that resistance is the ratio of voltage to current. So we would have 1 ohm is 1 volt per amp. That would be for the electric case. What would be the analogy for the hydraulic case? Well, we would have 1 volt. Instead of volts, we've got kilopascals. So it would be 1 kilopascal per, and instead of electric current, coulombs per second, or amps, we have liters per second. So 1 kilopascal per liter per second would be hydraulic resistance. And let's see, what would this mean? Well, we could imagine you got a great big pipe which would have very little resistance to the flow of current, and then we make that become much more narrow. Would expect to get a big resistance there. Meaning what? To get a certain flow rate, a certain number of liters per second, we would need a big drop in pressure, just like we need a voltage drop across a resistor to get current to flow. In a hydraulic circuit, if you want to think of it that way, for a large hydraulic resistance, which would mean a very thin piece of pipe or tubing, we need a very large pressure drop to get a given amount of flow rate, given number of liters per second. Okay, so that's the hydraulic analogy to electrical circuits, and we'll add to that later on when we talk about some other kinds of devices. But that just gives you a picture to think about. And of course, voltage then corresponds to pressure. And how could you get a large pressure in a hydrostatic system? You could do something like this. Here would be a pipe, and here would be our water level. We would have some height H, and the pressure P down here would be the density. Well, let's use mu for the density, which for water is about 1 kilogram per liter, times gravitational acceleration, G, which is about 9.8 meters per second squared, times the height H. So this is the classic formula for hydrostatic pressure. And so you could think this would be kind of like a hydraulic battery. You just have a tank, fill it up, and the higher you fill it up, the more pressure you get. And of course, as water drains out, then it runs out, and the hydraulic voltage, which is the pressure, goes down and down, kind of like a battery. Where does resistance come from? What's the source of it? Well, let's look at conductor resistance and the related quantity called the ampacity. So suppose we have a cylindrical wire conductor which has a length L and a radius R. So it has a cross-sectional area of pi r squared. And this is going to look like a resistor. So that's one way we can make a wire. That's very common, like in circuits and in household wiring, things like that. But like in circuit boards, so-called PCBs or printed circuit boards, the most common type of wiring is this rectangular shape. It looks something like this. And here we could have a height h and a width w and then a length L. And there the cross-sectional area would just be W times H. And that also is going to look like a resistance. The formula for the resistance of a wire is that it's equal to a constant that is characteristic of the material the wire is made of, rho, we call the resistivity, times the length of the wire over the cross-sectional area. That's the resistivity. How would we determine the resistivity? Well, we could take this formula, make a wire with a known cross-sectional area and length, and then solve for the resistivity. After you measure the resistance, then you would find resistivity is resistance times cross-sectional area over length. And what would the units of that be? See, R has units of ohms. Area is meters squared and length is meters. So this would be ohm meters would be the units. All right, so if you do that for different metals, say, and there's a table of some different metals and water in the PDF notes, but you find the best conductor is silver, and that has a rho value of 15.9 times 10 to the minus 9 ohm meters. Or you could call that nano ohm meters. Close behind is copper, which is 16.8, 10 to the minus 9. And another important conductor is aluminum. And that value is 26.5. times 10 to the minus 9. So that's quite a bit more resistive than copper. So obviously we don't use silver for a lot of wiring because it's so expensive, so rare. Although it is used for some very high precision circuitry where the cost is not as much of an issue as the lower resistance. Copper is quite a bit cheaper than silver and has only slightly more resistance. So that is by far dominates wiring for circuitry and household uses and things as smaller scale. Aluminum has considerably more resistance, not quite a factor of 2, but it's much cheaper and lighter than copper. And so this is for most circuits. And this is used extensively for power transmission, where you have transmission lines extending over many hundreds of kilometers, and you're using a lot of metal to make those conductors. And so the much lower weight and lower cost of aluminum more than offsets the advantages of copper. By the way, now these values are at a reference temperature of 20 degrees Celsius, because resistivity generally is an increasing function of temperature. So for copper, symbol for copper, the rho goes up by about 0.39% per degree Celsius. So resistance tends to go up with higher temperature. All right, let's see how to use this formula here. Let's say we have a copper wire, and so we're gonna have a resistance, which is going to be this rho value, which is here are 16.8, or to 4 digits, it's actually 16.78 times 10 to the minus 9 ohm meters. And let's take a length of 100 feet, which is 30.48 meters. And let's consider so-called AWG, American wire gauge wire of 14 gauge, which is very common in extension cords and household wiring. That has a radius of 0.814 millimeters. So this is our resistance is equal to our resistivity times the length, which is 30.48 meters, over the cross-sectional area, which is pi r squared. And this is going to be, because this is in ohm meters, and this is going to be 1 over a meter. Punch those numbers and you get 0.246 ohms. So 0.246 ohms for 100 feet of 14 gauge wire. Now imagine you use this in an extension cord. So here's a, say, 120 volt source, and then you've got this extension cord, and then out here you've got some load, say a weed whacker or something like that, that looks like an 8 ohm load. Okay, and now you're going to have some current flowing, current I, and this piece of wire, let's kind of emphasize that this is this extension cord. This has a resistance of 0.246 ohms, and then of course you need another piece of wire to return the current. That's also 0.246 ohms. And so we'll talk about in a future lecture resistors in series, that their resistance is just add. So this would be 0.246 plus 8 plus 0.246. That would give you a total resistance of 8.492 ohms. Okay, so the resistance of the extension cord plus the weed whacker now would be a little bit bigger than that of just the weed whacker alone. So what would be the current? The current would be the total voltage, 120 volts, over this total resistance, 8.492. And that's 14.13 amps. Okay, so what would be the voltage? Call that the load voltage here, V load. And there would also be a voltage across the wire. The wire, and there'd be another one up here, the same value. Let's see what those would be. Okay, so V load would be 8 ohms, using Ohm's law, 8 times I, 1413 amps, and that is 113 volts. Okay, and V wire would be 14.13 times 0.246. But we can see what happened here. We went from 120 volts at the source to the load only having 113 volts. We have a voltage drop, and that's due to the voltage drop in the wire conductors. And in fact, 113 over 120 is about 94%. So we're only getting about 94% of our source voltage. We're losing about 6% of our voltage due to the conducting leads of our extension cord having finite resistance. And correspondingly, we lose about 6% of the power. So if that was unacceptable to you, then you would need to use maybe, so this, typically a 14 gauge extension cord would be called a medium duty. A 12 gauge, which would be a fatter wire, would have a lower resistance, and so you could use a thicker wire, which would be more expensive and bulkier, etc., if that was very important to you. Okay, and so in these kinds of calculations, there's where the idea we talked about up here of, like for transmission lines, where the greater cost of more copper might really be the thing that keeps you from using copper for that purpose. So rho aluminum is about 1.6 times rho copper, about 60% more. But the density, kilograms per cubic meter of aluminum, is only about 30% of copper. So it's much lighter. And the price let's do it as $, of aluminum is about 25% the cost per kilogram of copper. So when you put this together, right, so you're going to have, in order to get the same resistance, we're going to need wires which have a cross-sectional area that's about 1.6 times as big. Let's see up here. Let's look at our formula. Right, so if this row goes up, then for the same length, the cross-sectional area has to go up by the same factor so that that ratio stays the same and we get the same resistance. Okay, so we're going to need about 1.6 times as many cubic meters of the aluminum as we would for copper to have the same resistance. But the mass is only about 30% as much, and the cost is only about 25% as much. And so if you punch all those numbers out, you get about 0.125, or about an eighth of the cost for aluminum versus copper. And of course, 8 times as much to use copper really is a showstopper in that situation. And you don't care about the larger volume of the aluminum because it's up on transmission lines and it's not having to fit in a box or something or in your walls. And aluminum's not quite as pliable as copper, but you don't really care about that for the transmission lines, but you would for household wiring. Now, since every conductor has some resistance, if we have a current I flowing through that, we know that it's going to consume power, Ri squared. What does that power do when it gets consumed by a wire? Well, it causes the wire to heat up. And as the piece of wire, as the resistor gets hotter and hotter, it transfers heat to its environment as it gets hotter than the environment. And so what's going to happen is it's going to get hotter and hotter until eventually this Ri squared heat being generated is equal to the heat that's being transferred thermally, and then you get into equilibrium. And that will be at some temperature. So you'll reach some temperature. Now, if T is greater than the melting temperature, what's also called the fusing temperature of the metal, then wire melts or fuses, which would be a bad thing generally, except we can use that to our advantage. So we can have, say, a little device. We got some thick wire here on the two ends of this device connecting into some circuit. And inside we've got, see, this is a piece of glass here, a little glass tube. And we've got a little thin wire in there which has a relatively high resistance. And so this then, let's say at 10 amps, that little wire will actually, its equilibrium temperature will be above its melting temperature and it'll burn out. Causes that to fuse. Well, then we call that a fuse. That's a little device that you can get and put in an electric circuit, and it's a sacrificial little piece of wire that will melt before the rest of the wire in the circuit gets hot enough to do any kind of damage. And what would that damage be? It wouldn't be the wire melting. In most circuits, we have wire and it has some insulation on it. Like plastic insulation. Oops. Insulation. And that's the temperature of that insulation being damaged is what really defines how hot you want to let the wire get. And this leads to the idea of ampacity. which usually is determined experimentally, but there's a pretty good formula for it, and that is that the maximum current is about 29 times the radius in millimeters to the 5/4 power. And that would give you the amperage, ampacity of the wire. And in the United States, that's formally defined in the National Electrical Code, but this formula gets you a pretty good estimate of that. So let's see. In the U.S., we use American wire gauge. And if you have N gauge wire, the radius in millimeters is 0.0635 times 92 to the 36 minus the gauge N over 39. So, for example, 16 gauge wire, which would usually be called light duty extension cord wire, has a resistance of 0.645 millimeters, and it has an ampacity of 16.8 amps. So you can see that if you use that in a 15 amp circuit, it would be getting pretty close to its ampacity. That's why it would be considered light duty type of wiring for an extension cord. All right, now, so using this idea, now with this kind of a geometry, the rectangular type geometry, we can see how actual circuit resistors are built. We start off with an insulating core, cylindrical core, usually made out of some kind of ceramic. And then on top of that, we run kind of like a spiraling conductor. This is all one piece. It would go up from behind and then continue around like this. And this would have some height in terms of this picture up here, so which would be like the thickness of the little copper strip, and it would have a width and of course a length from the spiraling, and we could change the width, make it wider or narrower, and we could change the length by changing this pitch of this spiral. And so we could then implement R is equal to rho L over the area, which would be the width times the height. And so that's called either a carbon or a metal film resistor. So if this little strip is made out of carbon, then it's a carbon film. If it's made out of a piece of metal, it's a metal film. And the way these are often manufactured is to just use so-called vapor deposition method to just coat this insulator by a solid layer of either the carbon or the metal, and then use some sort of either a mechanical tool or a laser to go through and cut out the regions where you don't want any metal. Okay, so that's how you would typically build a device like that. Now, this would also have an ampacity, usually defined in terms of a power rating. So if we go like back to the very first here, this little resistor here, this is an 1/8 watt resistor, which is very common for resistors used in electric circuits. So you'd have to make sure, right, that 1/8 watt, that would be P is equal to Ri squared, would be less than 1/8 of a watt. And so that would be effectively a limit on the current that could flow through it. So if you need more power handling capabilities, well, then you need to build your resistor with some other kind of technology that can handle the higher dissipated powers.